We've got data from Voyager, from Galileo, from Cassini, and even from Hubble. And one of the things that all those missions have in common is that they tell us the same thing about Uranus. Its upper atmosphere is unexpectedly thin. For decades, scientists assumed that the swings in Uranus's atmosphere were so extreme that it should have a thick atmosphere like Neptune or Jupiter. But as soon as Voyager flew by in 1986, we knew that wasn't true. Its atmosphere was way less dense than predicted, more like the thin atmosphere of Earth or Venus. And yet somehow this has not stopped our atmosphere from being hazy. So what's going on here? Well, now researchers think they might finally have the answer. They published their findings this week in the journal Geophysical Research Letters. And to understand it, we need to talk about how Uranus's atmosphere works. Like most other planets, Uranus's atmosphere is mostly hydrogen and helium, but with a lot more methane mixed in. And while we don't have any samples from Uranus's atmosphere to study up close, we do know its atmospheric pressure and temperature at different altitudes. And with that information, we can use physics to work out how dense the atmosphere should be at various heights. The further up you go, the lower the atmospheric pressure, so the gases would expand. But Uranus is also tilted on its side, so there are also some differences in gravity depending on where you are. All of that combined should give you a really thick atmosphere at the equator, which means there should be a lot of haze. But we don't see that. Uranus's atmosphere is much thinner than models predict it should be, and to make matters even weirder, sometimes hazes appear suddenly and unexpectedly in Uranus's atmosphere. There are spots where the atmosphere gets thicker and hazier, and then just as quickly disappears again. Scientists have been racking their brains trying to figure out why Uranus's atmosphere is so thin and why the hazes appear and disappear. One popular hypothesis was that the swings in Uranus's atmosphere from extreme cold to extreme heat had created a bunch of aerosols or tiny solid particles floating in the atmosphere. Aerosols tend to absorb or scatter light, which creates the haze we see. But if that was the case, we should see these aerosols uniformly distributed in the atmosphere, and that's not what we see either. In fact, the Voyager mission found that the haze is patchy. Some places are cloudy and hazy, and others are completely clear. There have been a few other ideas over the years, but none of them really explained both the thinness of the atmosphere and the sudden appearance of the haze. But the authors of this new paper think they may have solved the mystery. To figure out what's going on, they developed a new model of Uranus's atmosphere, and instead of trying to explain the constant haze, they modeled the sudden appearance of the haze, and they have a pretty simple explanation for it. Something inside the planet is pushing material upward very fast. Uranus rotates pretty quickly, and not only does this make the planet wider at the equator, it also creates powerful winds. But it turns out that those winds aren't strong enough to explain the features we see in Uranus's atmosphere. You would expect them to blow the haze around the planet, not create those localized patches. So something else must be happening. Scientists had already noticed that there seems to be some kind of upwelling happening at the surface of Uranus. This is visible in the sudden change in color from the deeper blues at the poles to the lighter blues and greens near the equator. That's because, as material wells up from the interior of the planet, it brings with it stuff that's less processed by sunlight. So it appears darker. And if this upwelling was strong enough, it could explain both the thin atmosphere and the appearance of the haze. So in their new model, the researchers assumed that this upwelling reached all the way up through the atmosphere, carrying dark material with it. At first, the results were not great. They could get the right amount of haze, but it wouldn't appear and disappear the way that it does on Uranus. Then they added in some extra physics to account for convection, basically the rising and falling of fluids due to differences in density. This turned out to be key. When they ran the model with convection, they got the sudden appearance and disappearance of the haze. In their model, material from deep inside Uranus rises rapidly through the atmosphere, bringing with it the stuff that creates the haze. Then once it reaches the top of the atmosphere, It spreads out and gets blown around by the winds until it's dispersed or sinks back down. This happens most rapidly at the poles where the atmosphere is thinner and the gravity is weaker, which is why the haze tends to appear first there. And when it's blown away, it reveals the lighter blue gases below. It's not quite the complete picture though. The team also needed to assume that there is some sort of barrier in the middle of the atmosphere that stops the upwelling material from reaching the surface. Otherwise the haze would just get thicker and thicker. They don't exactly know what this barrier is, but it might be related to the swings in temperature and pressure in Uranus's atmosphere. Maybe at a certain point the material is no longer buoyant enough to keep rising. But whatever it is, it seems to be strong enough to hold the atmosphere thin and keep the hazes from getting too thick. Overall, the researchers think this model explains all of the observations we have of Uranus's atmosphere. It's still a bit of a mystery, but it's looking less mysterious by the day. And it's not just cool to learn more about a faraway planet. Understanding how atmospheres work, whether on Earth or on exoplanets or anywhere else, helps us better understand our world. And that's why I love science. Thanks for watching this episode of Seashow Space. If you want to help us explain even more mind-blowing space stuff to the whole internet, we have a Patreon where the people who want to support the work that we do that, so that we can keep doing it. You can find it at our support page.